Good morning, everyone. Am I audible?
Yes, sir.
Yes,
Shall we begin?
yes, sir.
So please confirm that my screen is visible. Okay. Okay, let's begin. So yesterday we stopped at this place. We were proving uh, that if X is a non-linear space and if its dual space is separable, then X is separable. So while proving this, I missed one point here. So let me complete that point. I have already sent you the write-up about it, but what was the part that was missing that I will bring it out here. Okay, do you see my screen? Please confirm.
Yes, sir.
Okay, so here where I defined M. Okay, do you see this place? M.
Yes, sir.
Okay, so here I told you that M equal to span of this thing, span of all xn. So, but you know, span of xn is not countable. Okay. What we wanted to prove that X is separable. This means there exists a countable subset whose closure is X. Correct?
Yes, sir.
This is what we wanted to prove. But here I wrote span of this, but you know span of this is not countable. This is the problem. Okay, what we do there, we take span of this xn, but the coefficient we will take from rational numbers. Okay? Hello?
Yes, sir.
So what we do, we take linear combinations of xn, but in that linear combination, the coefficients come from rational numbers. Okay? And you all know countable union of countable sets is again countable. Therefore, this set will be countable. Without bar, this set will be countable. Okay? And when we take its closure, we define it as M and we show that this M is X. Correct?
Yes, sir.
So you all have that write up. You can make correction from there. Okay. So today is the last lecture of Unit 2. Then tomorrow onwards we will be focusing on Unit 3. Okay. So I have given you a note on reflexive spaces. So some of theorems I have mentioned, but then I just attach some some pages of a book. Okay, so you read those things, and if you have any doubt, please ask me.
सर
So, with this,
सर लास्ट स्टेटमेंट आप बोल रहे थे वो
कौन सा
स्टेटमेंट
last?
थोड़ा अभी जो वो स्पैन वाला
हाँ, स्पेन वाला, ओके, नहीं समझ में आया?
जी
Okay, what is span of say x1, x2, dot 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 xn? Say, what is the span of this? Span of any set is linear combination, set of all linear combinations, set of all linear combinations of x1, x2, x. Correct? Is it correct? रामजीवन,
यस सर
हाँ तो बोलो भैया, जब मैं पूछ रहा हूँ तो उसका थोड़ा बोलिए ना। ये सही है यहाँ तक?
यस सर
अभी मैंने बोला कि जब हम सेट ऑफ ऑल लीनियर कॉम्बिनेशंस लेंगे तो जो ये स्पैन वाला ये जो सेट बनेगा ये तो अनकाउंटेबल इनफाइनाइट सेट है, इसकी कोई गारंटी नहीं है कि काउंटेबल होगा। स्पैन में आप लीनियर कॉम्बिनेशन क्या होता है? लीनियर कॉम्बिनेशन इज एन एक्सप्रेशन ऑफ दिस फॉर्म। So where k belongs to z plus, okay, correct?
यस सर
Where this alpha I comes from a real number. You know r is uncountable. So this span is again uncountable set. But you need a countable set. So what you do, you take this alpha I from Q. Okay. हेलो,
जी सर
तो इसीलिए मैंने उसको स्पैन नहीं लिखा, उसके नीचे ऐसे क्यू कर दिया, ठीक है? Where span sub q x1, x2, xn means set of all linear combinations of this with rational coefficients. Okay,
यस सर
अभी ठीक है? And
ये
you know q is counted. हाँ क्या?
ये पर्टिकुलर केस बन जाएगा
पर्टिकुलर केस किसका?
मतलब ये कोई हम जनरल स्पैन की बात करेंगे तो वो हमेशा काउंटेबल नहीं होगा
हाँ, हमको काउंटेबल चाहिए, इसलिए हमने ऐसा लिया। But what we did, we exploit the properties of q. You know q bar is r. This is correct? Is this correct?
Yes, sir.
Closure of q is r. So when we take span q x1, x2, so on, and when we take bar of this, we will get span of x1, x2, x. Correct? है ना? Okay.
यस सर
Let's move ahead. Next thing is reflexive spaces. So in your vector space course, you have learned about this thing, the second dual. Do you know about second dual? Second dual space. If you do not know, let me recall it for you. So suppose we have a vector space X. What we do, we then find we construct another subspace, another space, vector space, uh, which is called dual space, and which is, say we will call it algebraic dual space. And what is that? Algebraic dual space is set of all linear functionals. Okay, so we denote that by X star, algebraic dual space. Correct? So from X we go to X star. So this is again a vector space. Okay? Then what we do, we do same thing with the X star. Now X star is a vector space. We look at its dual. So this means dual of this. This is called second algebraic dual space. This is again a vector space. In your linear algebra course, you have already seen this for so in linear algebra course you were interested basically in finite dimensional vector spaces. Okay, so for every finite dimensional vector space X, we have X is isomorphic to say X, so we denote it X star star. You all know this. And do you know how do we prove this thing? Any idea? So the best way to prove this was, so we fix some X naught in X and we define map G X naught from X star to K given by, so you all know the elements of X star are linear functionals. So when we act G X naught to a functional F, we define it as like this. So this is again a linear functional, correct? So then what you do, you define a map X to X star star by this thing. So from here, this Gx naught is a linear functional, means it belongs to X star star. So linear function, this is linear functional on X star. Therefore, this is an element of second dual space. So you define a map from X to X star, which sends each X to Gx. So in this way, so you then proved that this map is 1, 1 on 2 and it's linear, and hence X and X double star both are isomorphic. So this is what you have done already in your linear algebra course in second semester. So you know this part. I will not talk about too much. Okay, what I will do, I will not talk too much about it. So what I do, so here you all know we are interested in bounded linear functionals. Okay, so far we are interested in bounded linear functions. For that, what we do, we take a norm linear space. Okay, and one more thing. So here, what we have recalled this for finite dimensional vector space. We do not know is this true for infinite dimensional vector spaces so far. We do not know. I think you have not seen this for infinite dimensional vector spaces. Okay, but this is not the case in infinite dimensional space, but a little similar thing you can say, but not exactly this. We will see what we can say for infinite dimension. Okay. So now take X a non-linear space. You know the dual space. Dual space here we mean by a dual space the space of all bounded linear functional on X. Correct? Similarly, we have X, we have X dash. Now this is again a vector space. This is vector space. And in fact, you know this is Banach space. No matter X is Banach space or not. Now you do one thing. Take dual of this dual space and call it X dash dash. This is second dual. Again by similar regions, this is a vector space. Okay. So reflexive means if X is isomorphic to X double dash, then such a space X is called reflexive space. Okay. So all finite dimensional vector space, all finite dimensional normed spaces are reflexive spaces, because you know in finite dimensional space, finite dimensional spaces, all linear transformation or operators are, please complete this. Everyone,
Yes, sir.
complete this sentence. In finite dimensional spaces, all linear operators are
फाइनल इक्विवेलेंट या बाउंडेड होते हैं सर.
bounded.
सर प्लीज एक फिर आप रिपीट करिए.
हाँ सही बोले ना आपने, बाउंडेड. In a finite dimensional space, every linear operator is bounded.
Yes, sir.
Correct. So this means X dash is same as X star. Correct. And similarly, regions X double dash is same as X double star. And you know, for finite dimensional vector spaces, X is equivalent to X star star. So this implies X is equivalent to X dash dash. So every finite dimensional vector space is reflexive space. Okay. So we do it similarly. We define for each given X in X, we define X dash Gx from X dash to K by choosing X by define. So we define Gx by this Gx f equal to fx, and this is true for all f in X dash. So since f is bounded, Gx is bounded. You know, since f belongs to X dash, and X dash is the space of all bounded linear operators, this implies Gx is bounded. So let's see via a theorem. See the theorem. Okay, for every fixed X in X. So here X is a non-linear space. The functional on X dash, what is that functional? The functional this, given by Gx of f equal to fx. So if you see my notes, I wrote f maps to fx. This is same as Gx f equal to fx. Okay. If some of you do not know this fact, then this is simply a notation. Okay. So And for all f in this, for every x in x, the functional gx is bounded on x dash and norm of gx is same as norm x. And similar thing, we will, whatever I said here, we will define this for x dash. Furthermore, the mapping phi from x to x dash dash given by phi x equal to gx is an isometric isomorphism of x the subspace of x dash. So here see what this part says. This part says that x is isomorphic to x hat. It is not saying that x is isomorphic to x double dash. Okay. Here for finite dimensional spaces, this was true. X was isomorphic to x dash dash. Okay. Hello. Do you see this? For finite dimensional vector spaces, x is isomorphic to x dash dash. But in general, it is not true. In general, x is isomorphic to a subspace of x dash dash. Okay. So let's prove this. It's very easy. So I'll skip some part. So linearity of G is easy to see. Gx is linear. So how? Take two elements from x dash f1 f2 in x dash and alpha beta in k. So for proving Gx is linear, you have to prove Gx alpha f1 plus beta f2 is same as alpha Gx f1 plus beta Gx f2. This is what you will do. Okay, consider this part, left hand side, Gx alpha f1 plus beta f2. By definition, this is nothing but what is it? Please tell me. Jyoti?
G of f is equal to f of x हो जाएगा.
हाँ, f क्या है यहाँ पर? f ये पूरा का पूरा है. So alpha f1 plus beta f2 of x. But you know how do we define this? This is nothing but alpha f1x plus beta f2x. Okay? And this is nothing but alpha gx f1 plus beta gx f2. And this is what we wanted to prove. Okay? So for boundedness of gx, what we do, we just consider this. So by definition, this is nothing but f of x. But you know this inequality. This is true for all f in x dash. And since f is bounded, gx is bounded. Clear? This implies gx belongs to x dash dash. So there was one equality, this equality. Let's see this. So now let's compute gx. By definition, what is norm of Gx? What is norm of
Supremum.
Gx? Supremum
x यहाँ पे f हो जाएगा, f belong to x dash.
f belongs to x dash, f is non-zero, mod of dx of f by norm f, correct? And this is supremum f in x dash, no f non-zero, this is fx by norm f. So now do two things. So you know fx is less than equal to norm f norm x. So from
Right,
this
sir.
from this inequality, norm gx less than equal to norm f. From this inequality you have, correct? And for other inequality, what you do, you take a particular kind of f, choose f tilde in x dash such that f tilde x equal to norm x. And you know, for this you have norm f tilde equal to 1. Choose this x, and since you know supremum of mod of fx by, oh sorry, here by norm f, where f comes from x dash, f is not zero. This is obviously, because this is supremum, this is greater than equal to f tilde dash x by norm f. But you know norm f is 1, f tilde x is norm x, so this is norm x. And this supremum, this part is nothing but norm of gx. So this implies norm of gx is greater than equal to norm x. And here, oh sorry, here I did a mistake, typographical mistake. This is x. See why? When you put this inequality here, it will be less than equal to norm f norm x by norm f, norm f get cancelled, you will get norm x, correct? Any doubt?
सर आप कुछ लिख रहे हैं?
हाँ, नहीं दिखाई दे रहा क्या?
जी सर, शो ही नहीं हो रहा है.
शो तो हो रहा है. हेलो खुशबू, क्या आपको भी नहीं दिखाई दे रहा?
तो मेरे में तो दिखा रहा है.
दिखा रहा है रामजीवन, आपका नेटवर्क अच्छा नहीं है इसका. ओके, इज इट करेक्ट? सो फार इट्स ओके. कोई बोलिए ठीक है या नहीं है, या मुझे रिपीट करना है?
लेस देन और ग्रेटर देन हो गया तो इक्वल दिखा देंगे.
तो ये दो लेस भी हो गया, इक्वल भी हो गया, ग्रेटर देन भी हो गया, तो इक्वलिटी आ गई. ठीक है. So from this and from this, from gx go to norm x. Second thing is this part, pi given by this is an isometric isomorphism. So this is also very easy. So for this you have to show that pi is linear and pi preserves norm. Pi preserves norm. And if pi preserves norm, then it is clearly it will be injective. You have to show these things. So why pi is linear? So first of all, pi is defined from x to x dash dash given by pi x equal to gx. Okay, linearity, let's see linear. So for this, take two elements from x, say x1 comma x2 in x and alpha comma beta in k. So then alpha x1 and beta x2 of pi of this, and you want, so our claim is this is pi x1 plus beta pi x, correct? This is what we want to show. So consider this left hand side, pi alpha x1 plus beta x2. By definition, it is g alpha x1 plus beta x2. Okay? Hello?
Sir.
Is it correct? Is it correct?
Yes, sir.
Okay. So, so this G, okay, this pi is a map from x to x double dash. This means pi is so pi x is an element of x double dash. So it will act on, so
A
let me
function.
write this again, a linear functional. Okay, so this. So, but by definition, this is f of alpha x1 plus beta x2, and f is linear functional. So this means this is alpha x1. हाँ बताओ.
तो पाई का जो एलिमेंट होगा, जैसे एफ ऑफ एक्स लेंगे, पाई ऑफ एक्स लेंगे, तो एलिमेंट एक्स का होना चाहिए.
x
उस पे
from x. देखो
हाँ.
पाई क्या, पाई फ्रॉम x to x डबल डैश है, ठीक है. ठीक, आपने एक एलिमेंट x का उठाया, आपने पाई एक्ट कराया x पे, तो ये अब कहाँ चला जाएगा, ये चला जाएगा x
डबल
डैश में, सॉरी x डबल डैश में. x डबल डैश में क्या होते हैं एलिमेंट,
फंक्शन.
फंक्शनल्स होते हैं. सो दिस मींस दिस इज अ फंक्शनल. So this means this pi x will act on f. Okay.
ओके सर. हाँ.
आई बात समझ में?
यस सर.
Okay. So let's remember this. So you get this part. So from here alpha fx1 is nothing but alpha of gx1 gx1f plus beta of gx2f, but this is gx1 plus beta gx2f. So this is okay. So far we are here, but you know alpha gx1 is pi of pi of, okay, alpha gx1 is pi of x1, gx2 is pi of x2, and we are done. Correct? So this implies pi alpha x1 plus beta x2 equal to alpha pi x1 plus beta pi x2. So pi preserves now. We have already seen this here. So let's see it again. Pi preserves now. This means norm of pi x would be norm of x. This is our claim. See this y. So take any point in x, and this is true for all x in x. Okay. So fix x. Consider pi x, By definition, this is norm Gx. But we have already seen norm Gx is norm X. Okay. This means pi preserves. Now, this implies pi is an isometry. This implies pi is injective. Okay. So, we are done. So this means pi is an isometry and an isomorphism. Okay, not isomorphism. Let me omit this. I did not write it in correct way. So for isomorphism, I have to show that it is onto. Okay. So what we do for isomorphism? Isomorphism means it's a linear operator. It should be 1, 1, and it should be onto. Correct? This is the definition for isomorphism. Is it correct? Hello?
Yes, sir.
Okay, but so far what we have proven is it's linear operator, it's 1, 1. We didn't say anything about onto. So, but we know if pi is 1, 1, okay, if pi is 1, 1 and this is the map from x to x double dash, then clearly pi is onto its image. Okay, so this is an into map. If I replace x double dash by pi of x, this is on. Okay, so this means pi is isometry and an isomorphism onto its image. Okay, onto its range or onto its range. And you know, range space is a subspace. Okay, so we are done. We just proved that X is isomorphic, which we call X. Okay, this pi is called canonical mapping. This pi is called canonical mapping, and this Gx is called functional induced by the vector x. So now a definition. So if x dash, x double dash is same as pi x. Okay, if x double dash is same as pi x, then x is called a reflexive space. Okay, so this means a space which is isomorphic to its second dual space. That space is called reflexive space. So let's see some observations. Okay. So you know, if we have a non-linear space X a non-linear space, what can you say about X dash? Hello? Ramjivan,
Sir,
if X is a non-linear space, what can you say about X dash? Is it complete or it need not be?
if com
So let me ask
complete,
it another way. So we have a non-linear space and we define set of all bounded linear functional from X to Y. X and Y both are non-linear spaces and Bxy is the set of all bounded linear operators. So Bxy is complete if Y is complete. Have you seen this result?
yes, sir.
Okay, so what is X dash? X dash is nothing but Bxk, bounded linear functionals. So when Y is replaced by K, we call these operators as linear functional. Correct?
Yes, sir.
And you know K is complete.
Uh, so
So we are taking only complete fields. We are working on complete field. Okay? So K is complete. So this means by above result that I just mentioned, this Bxk, which is nothing but X dash, is complete. So from this, from this, X dash is Banach space. But then X double dash, by same reasoning, X double dash is also complete. Okay? And you know two non-linear spaces are isomorphic. Then if one is complete, another will be complete. The other will be complete. Jyoti,
Sir.
any doubt?
Yes, sir. No, sir.
हाँ क्या अच्छा नो ठीक है okay so this means if x dash x double dash I'm saying that x is reflexive this means by definition x is isomorphic to x double dash correct
Yes, sir.
if x double dash is complete x is complete so this means all reflexive spaces are complete reflexive implies complete. So what about converse exercise? Okay. So if a space is not complete, then it is not reflexive. Okay. Now another thing. Question: is R2 over R, this is a vector space, reflexive? Is this reflexive, Vasudev? Soumya Saxena. Soumya, are you there?
Yes, sir.
Now, so here is the question: is R2 over R is reflexive? हेलो,
यस सर, तो सोच रहे हैं।
हाँ ज्योति,
सर आर तो रिफ्लेक्सिव होता ही है
होता ही है
एलिमेंट।
मतलब
सर आर
कैसे होता है?
रिफ्लेक्सिव होता है सर।
कैसे होता है
सर हम तो रिलेशन
उसका?
के थ्रू देख रहे हैं।
कौन सा रिलेशन? अच्छा, ओ वो दोनों अलग हैं ज्योति।
यस
आपने वो
सर।
रिफ्लेक्सिव क्या एक्स कॉमा एक्स बिलोंग टू आर वाली बात कर रहे हो क्या?
यस सर,
सर।
नहीं 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 नहीं, नहीं,
कहाँ पे
ये
दिखाना है रिफ्लेक्सिव प्रॉपर्टी?
वो रिफ्लेक्सिव अलग है।
हम्म,
वो जो आप इक्विवेलेंट रिलेशन में पढ़ते हैं वो रिफ्लेक्सिव अलग है। नेम सेम है, वो रिफ्लेक्सिव रिलेशन है, ये रिफ्लेक्सिव स्पेस है। Here it was reflexive relation,
यस
reflexive relation, और यहां पर है ये रिफ्लेक्सिव स्पेस। दोनों बिल्कुल अलग है। कैसे? यहाँ पर ये रिलेशन मींस एक एक दो, अगर हमारे पास ए और बी दो सेट है, सॉरी ए कोई सेट है, ए टू ए हमने एक रिलेशन डिफाइन किया, वो रिफ्लेक्सिव होगा। ये एक मैप की प्रॉपर्टी है, नॉट मैप, एक रिलेशन की प्रॉपर्टी है, ठीक है। ये एक किसकी प्रॉपर्टी है? रिलेशन की।
चाहिए तो
और ये एक स्पेस की, ये सेट की प्रॉपर्टी है। यहाँ पर सेट से मीनिंग नहीं है, ये किसकी प्रॉपर्टी है? रिलेशन की प्रॉपर्टी। और ये एक सेट स्पेस, वेक्टर स्पेस की प्रॉपर्टी है, ठीक है। तो दोनों बिल्कुल अलग है, उन दोनों के बीच में कोई रिश्ता नाता नहीं है, बस नाम सेम है, ठीक है।
ओके सर।
के नाम के बहुत सारे लोग हो सकते, नहीं हो सकते, जिनके बीच में कोई रिश्ता नाता ना हो, बस ये दोनों ऐसे समझो, ओके। अभी बताओ, ये इसका आंसर मैं पहले दे चुका हूं, अभी क्लास स्टार्ट होने के साथ साथ ही मैं आंसर दे चुका हूं इसका। कोई बता सकता है ये रिफ्लेक्सिव है या नहीं है? प्रिया उपाध्याय, प्रिया।
यस सर।
हाँ, R2 over R इज रिफ्लेक्सिव और नॉट?
सर R2 का सेकंड डुअल स्पेस तो R2 ही होगा ना?
कैसे? ये क्यों ऐसा हो? कहाँ पढ़ा आपने? रामजीवन,
जी सर, हम सेट ऑफ ऑल बॉन्डेड लीनियर ट्रांसफॉर्मेशन लेंगे, R2 to R लेंगे, R कंप्लीट इसलिए वो कंप्लीट हो जाएगा।
हाँ,
और वही
हमने हमने ये नहीं कहा कि कंप्लीट इंप्लाइज रिफ्लेक्सिव, ऐसा ट्रू नहीं है ना, ऐसा जरूरी नहीं है।
सर
ये
स्केलर्स
देखिए यहाँ
तो
पर
बाहर से आ रही है।
एक बात बताइए, यहाँ पर लिखा है रिफ्लेक्सिव इंप्लाइज कंप्लीट, दिख रहा है आपको?
यस सर, यस सर।
कन्वर्स नॉट ट्रू, आपने बोला कंप्लीट होगा, मैंने बात मान लिया,
ठीक है।
लेकिन वो रिफ्लेक्सिव नहीं देगा। अगर आप थोड़ा सी ध्यान से सुनते लेक्चर को, तो मैं ये आंसर पहले दे चुका हूँ। कहाँ पर? यहाँ पर, ये देख रहे हो क्या लिखा है? क्या लिखा है ये?
सर मेरे पास तो शो ही नहीं हो रहा है।
अच्छा, किसी के पास शो नहीं हो रहा है क्या?
सर हो रहा है। Every
क्या
finite
लिखा है बताओ?
dimensional vector space X is
So
isomorphic to double star.
डबल स्टार, सो ओके, सो फाइनाइट डायमेंशनल स्पेसेस में एक्स डबल डैश और एक्स डबल स्टार दोनों सेम होते हैं।
हाँ।
Yes
और
sir.
मैंने बोला एक्स इज आइसोमॉर्फिक टू एक्स स्टार स्टार, सो एक्स इज आइसोमॉर्फिक टू एक्स डैश डैश, करेक्ट?
Yes.
कोई दिक्कत इसमें?
No, sir.
Okay, then this means R2 is reflexive because it's a finite dimensional vector space. Okay. Okay, let's move ahead. तो ये आपको पता चला क्यों रिफ्लेक्सिव है. ओके तो इसके लिए एग्जांपल आपको ढूंढना है कि कंप्लीट है तो वो रिफ्लेक्सिव नहीं है. स्पेस विच इज कंप्लीट बट नॉट रिफ्लेक्सिव. ओके नेक्स्ट थ्योरम. A normed space is isometrically isomorphic to a dense subspace of a Banach space. This is very easy. You see this? A normed space is isometrically isomorphic to a dense subspace of a Banach space. Okay, let's. So, if you remember the first theorem that we proved today, it is written here. Okay, let's see what is written. It is written that the mapping pi from x to x double dash given by pi x, this canonical mapping, is an isometric isomorphism of x onto the subspace of x dash dash. Correct? ये हमने प्रूव कर दिया है. Okay. If you prove that this x double dash is a Banach space, we are done. But you know this is true. You know that x double dash is Banach space. Why?
Dash or
X is a Banach space and X is isometric.
x Banach space तो है ही नहीं. हमने तो बोला नहीं x Banach space. हमने कहा x normed space है. Normed space x. Okay, x is a normed space. What can you say about x dash? अभी कुछ समय पहले बात हुई थी इसके बारे में. हाँ हेलो
yes, sir.
बताओ.
सर अभी तो आपने बताया था ना बी एक्स के और जहाँ पे के
हाँ तो x dash कंप्लीट है.
वाई डैश.
सिमिलर रीजनिंग x डबल डैश भी कंप्लीट होगा. ठीक है. Okay, but you know from that theorem, the first theorem, that x is isometrically isomorphic to pi x. You know, correct?
Yes.
Pi x is a subspace of x double dash. Pi x is a subspace of x double dash. Correct? But we do not know that pi x is complete or no. Not. We only know that pi x. We only know that x double dash is complete. This is complete. This is a Banach space. X double dash is a Banach space. What you do now, take pi x closure, and you know if y is a subspace of x, then y bar is also a subspace of x. Correct? Closure of a subspace is again a subspace. Correct? So
Yes,
this
sir.
means this is the closure of pi x is a closed subspace. Closed subspace of x double dash. Correct? Okay? Hello?
Yes, sir.
हाँ या ना कुछ बोलते रहो. Okay. So you also know that a closed subspace of a Banach space is again Banach space. Closed subspace of complete space is complete.
Yes, sir.
So this implies pi x bar is Banach space. Is Banach. Okay. So x is isomorphic to pi x. Clearly, pi x is dense in pi x bar. Pi x is dense in pi x bar. Is it correct? Is this correct? ये तो ठीक है ना. एक मैंने सेट लिया y, मैंने कहा y डेंस होगा y बार में. क्यों? क्योंकि y बार इक्वल टू y बार. So pi x is dense in pi x bar. This is obviously true, because closure of pi x is nothing but pi x bar. नहीं समझ में आया?
सर जैसे एक्स बार को आर के इक्वल दिखाते हैं, इसका क्लोजर इसी के इक्वल हो जाएगा.
क्या क्या बोला?
पाई एक्स का क्लोजर लेंगे तो पाई एक्स बार के इक्वल आ जाएगा.
हाँ, तो यही तो डेंस की डेफिनेशन है ना? इसकी डेफिनेशन यही है. So this means pi x is dense in pi x bar and pi x bar is Banach space. So this is true. X
That's true.
is isomorphic to a dense subspace of a Banach space. So this dense subspace is pi x and this Banach space is pi x bar. Okay? Understand?
Yes.
लास्ट में क्या है?
लास्ट में कहां पर? एक मिनट, मैं फिर से रिपीट कर रहा हूं. हमारे पास x डबल डैश बेनाक था, ठीक है? x डबल डैश इज बेनाक, क्लियर है?
सर
ओके. ये हमने प्रूव किया था x इज आइसोमॉर्फिक टू पाई x, जिसको हमने x हैट कहा था. दिस इज आइसोमेट्रिकली आइसोमॉर्फिक टू x हैट और पाई x. तो मैं इसको x हैट लिख देता हूं. क्लियर? ये ठीक है?
यस सर.
x hat was subspace of
एक्स
double dash. Clear?
यस
If
सर.
I take closure of x hat, that is pi x. If I take closure of this is a closed subspace of x double dash. Since x double dash is complete, this closed subspace is also complete. This implies x hat is Banach, x hat bar. Clear?
यस सर.
So, and x hat is dense in x hat bar. Clear? ये तो सिंपल सा है ना. x hat dense होगा x hat बार में.
हाँ सर, भी देखा था ना.
ये डेफिनेशन है. So why is it true? Because closure of x hat is x hat bar.
Yes.
Okay. So this means we are done, because x is isomorphic to a subspace, to a dense subspace of a Banach space, where what is that Banach space? Banach space is X hat bar, and what is that subspace? That is X hat. So X hat is isomorphic to, sorry, X is isomorphic to X hat. Then, okay, so it completes the unit 2. So there are few other results that you will read yourself. Okay, so tomorrow onwards I will be focusing on unit 3. Okay then, see you.
सर
Drop
ये
your
लास्ट
attendance.
था यूनिट 2 का.
हाँ, यूनिट 2 का लास्ट रिफ्लेक्सिव स्पेशल. ठीक है.
ओके सर.
ओके.